Now, to prove the Fourier integral theorem, that is this result, we need to we need a result of Jordan lemma. The lemma is very simple. Suppose G is a bounded variable function over an interval 0 delta. Then the limit as alpha goes to positive infinity 0 delta gt sine alpha t divided by t dt. This limit is the right limit of g at 0 multiplying half of pi. This is the so-called Jordan lemma. Now we need to prove this Jordan lemma. So because g is bounded variation, and that is g is the difference of two increasing functions, so we can treat the increasing function separately and then collect the result together. Therefore, we assume that g is increasing. Proof. It's sufficient to prove the case. G is increasing. Now, so we make this assumption. So this is the interval 0 delta. Because the right limit, note that the how can we write the right limit g 0 plus? How can we write this? Because as the increasing function, the limit always exists. By the monotonicity bounded principle, we know that the limit of an increasing function at the point always exists. Okay, the one-side limit, the limit might not exist if the left limit and the right limit are not coincided. But at least the one-side limit exists, so we can write this g0 plus. So the limit exists. Therefore, we might assume that for any epsilon positive, we can take h positive and smaller than the delta, such that gt minus g0 plus, that is the right limit at 0, less than epsilon for any t in the interval 0h. Okay, so we take such an h, then our integral 0 to delta gt sine alpha t divided by t dt. This integral can be written by the sum of three terms. These three terms are given by 0h gt minus g0 plus, then sine alpha t over t dt plus g0 plus 0h sine alpha t dt. Finally, h delta integral gt sine alpha t dt. Okay, the integral are written in these three terms. So let's have a look at one I2 and I3. For I3, the last term goes to 0 as alpha goes to infinity. Why this goes to infinity? Because h is positive, therefore gt divided by t is integrable. Okay, so by the Riemann-Lebesgue lemma, we know that the last integral I3 goes to infinity. Okay, and for the second integral I2, we know that the integral in I2 can be made. We make a change of variable for the integral I2 become g0 plus multiplying 0 alpha s sine s divided by s, then ds. Alpha t, let alpha t be s, then the integral becomes an integral of s. Then when alpha goes to infinity, this becomes the integral of sine s over s from 0 to infinity. When alpha goes to infinity, okay? No, sorry, not alpha s. I have a mistake. This should be alpha h. Sorry, alpha h. Alpha h. Then sine s ds. But when alpha goes to infinity, the upper limit of the integral, that is alpha h, is infinity. So we know that this integral is half of pi. Of course, we have not computed this integral. Using the technique of integral with a parameter, we can solve that this integral is a no integral. The value of the integral is half of pi. Therefore, the I2 term goes to the result declared in the Jordan lemma. That is I2 goes to g0 plus half of pi. So if we can prove that I1 goes to 0, if I1 goes to 0, then the result is correct. Okay, because the integral in the lemma divided into I1, I2, and I3. I2 converts to the number in the lemma, and if I1 and I2 convert to 0, then the result is valid. But we already know that I3 goes to 0, so we only need to study I1. Okay, we study I1 in the next page. So to study I1, we need the second intermediate formula for integral. That is also called Bonnet theorem. So let's call the Bonnet theorem. Bonnet theorem says that if f is Riemannian integrable over an interval AB, and g is increasing and non-negative, then there is a xi in the interval AB such that AB fg equal gb integral from xi to b f. This is the second integral mean value theorem, also called Bonnet theorem. We need this result. I don't know whether you have studied this result in mathematical analysis 1, but we need it here. So from this we get the absolute value of I1. That is, I1 is the integral from 0 to h gt minus g0 plus then sine alpha t dt. This is I1. So because g is increasing, our g is increasing, g is increasing, and therefore gt minus g, the limit at 0 is non-negative. So this term as a function of t is non-negative and increasing, and this term is integrable because although t is at the position of a denominator, when t is 0, there are some problem. But fortunately, when t goes to 0, it has a limit, maybe alpha. Yes, the limit is alpha as t goes to 0 from the. Okay, so this function can be, is not defined. Sine alpha t over t is not defined at t equal to 0, but we can define the value of this function at t equal to 0 by alpha. Then this function is a continuous function on the closed interval 0h. Therefore, it's integrable. Okay, so this for this integral we can apply the Bonnet theorem and obtain that this is equal to gt minus g0 plus, then for some c, then h sine alpha t dt. Okay, and this is precisely gt minus g0 plus absolute value, then absolute value of c h sine alpha t dt. Okay, but the first factor is less than epsilon by our choice of h, because c is belongs to c is a point in 0h. Okay, therefore we know that when t is not greater than h, then this is less than epsilon by our choice of h at the very beginning. We choose an h here. Okay, so that gt minus g0 plus is less than epsilon. So we know that c is so we know that when t for here is h. I make a mistake. Here is h. So gh minus g0 plus is less than epsilon. Okay, and this term is a bounded term. This term is now we explained why this term is bounded, independent of alpha. So we know that ch sine alpha t dt by a change of variable, that is alpha c alpha h sine s ds. Because the c here depends on alpha. For different alpha, this is a different function. So applying the Bonnet theorem, the resulting c here might depend on alpha. If c is independent of alpha, this is an easy problem. But c might depend on alpha, so we need to be more careful. But this is precisely capital F alpha h minus capital F alpha c. Okay, but what's the capital F? The capital F is capital F x is 0x sine s over s. We use this function. Then we know that capital F is continuous. It's continuous for 0 to positive infinity. And the limit at infinity, when x goes to infinity, capital Fx, that is the integral from 0 to infinity sine s ds. This integral is pi over 2. So f is a continuous function, has a limit at infinity. Therefore, the capital F is a bounded function. Capital F is a bounded function. There is some m. Capital F x less than some m. For every x, no negative. So this two terms, therefore the difference of these two terms will not greater than 2m. So this means that this term will not greater than 2m. So we conclude that when alpha is large enough, the absolute value of I1 will not greater than 2m multiplying this epsilon. Therefore, this tells us that I1 goes to 0 as well. And concluding the proof of the Jordan lemma. Okay.